Hi there, and welcome to your first pre-lab video for General Chemistry 1 at your college in Pennsylvania. I'm Dr. William Steele. I'm the coordinator of the General Chemistry course and laboratory here at the college. And today I'll be walking you through some of the important information I'd like you to have on hand and know before starting your first laboratory exercise of the semester. So our first exercise is the fundamentals of measurement, where we're going to focus on two goals or two outcomes that we would like you to attain through this exercise. First is to learn how to use our measuring tools correctly. There are a variety of different tools or instruments that a chemist would use to measure or collect data in the laboratory. Each has a different scale, and you have to know how to use that scale correctly. So that's one of our goals today. The other is when we combine measured values from two different tools that we've used to measure items in the laboratory, how do we report the calculated result correctly? So both of these goals touch on significant figures and the rules of measurement, topics covered in Chapter 1 of our text in the lecture portion of the course. As a bonus for sitting through the video today, I'll also answer the pre-lab questions for you so that you can come prepared with those when you arrive at lab and earn full credit for your pre-lab exercises today. All right, one of the tools that you'll be using today is a meter stick that has 4 different scales on it. The first simplest scale, labeled side A, has no markings on it at all. So it's just 1 meter, and it could be used to measure anything on that scale. The second side, B, is marked off in the decimeters, or tenths of a meter. The third side, side C, has the centimeters marked off, and the fourth side, D, also has the millimeters noted on it. When you use one of these sides, you can report a length that you've measured to a different degree of accuracy. It's all about the estimation or the guess that you make using the scale. Let me demonstrate for you. I've got a rectangle drawn on the board here, and suppose I would like to calculate the area of this rectangle. I need to know the length and the width to do that. Pretty easy, right? Let's use our meter stick with no markings, the side with no markings on it. If I hold the meter stick up to it, I have to totally guess how long this rectangle is. So I have really no idea. And so I'll say, okay, maybe it's about 4/10 of a meter long. 0.4 meters long. You might have guessed 0.3. You might have guessed 0.5. Those are both acceptable guesses. A guess that is not allowed, or an estimation that is not allowed, would be something like saying a third, 0.33, or going any further than 1 decimal place. These are improper uses of your scale. The rules for using any measuring device with a marked scale are to record all of what are called the known places of certainty, plus 1 guess, 1 estimation, where you mentally divide the end of that, or the scale, the last 2 markings, into 10 divisions and estimate how many increments are included in the measurement. If I turn to side B and go back and measure my rectangle on the bottom now, I can now see, oh, it was not quite 0.4. Here's my, it's hard to see, I appreciate on the video. Here's my 0.3, here's my 0.4. So I now know that it's 0.3 for sure, and I'm going to mentally divide the area between 3 and 4 into tenths and say, okay, I think it's about 5. This last place is our guess. We are required to do it because we have the ability to see that it's not exactly 3 and not exactly 4. Right? And so every measurement that you see reported in a scientific piece of data has these guesses involved in them. Okay? Now let's measure the width of this rectangle, or the height of the rectangle. Okay? Again, if I use the top, the side A, I've got really no idea. I'm going to guess it's about 2/10, so I'll say 0.2 meters. Okay? Let me use a more accurate side. How about I use side C, where my centimeters are clearly marked out? Now I can see that in centimeters, it falls between 23 and 24. So that would be 0.23. And again, I'm going to have to guess at that last place. I think it's maybe 2, 3, 4. Maybe not quite a half. But you are welcome to make any legitimate, reasonable guess as to that last significant figure of the measurement. Okay? If you think it's 0, please put the 0 there. That is an important part of the measurement that you would have. So that's goal number 1. Using our tools correctly. Again, you measure all of the known places of certainty, and then you must estimate where the last digit falls on the scale. All right? Now this is not needed when you use one of our electronic balances. Let me address that briefly, because the electronic balance is already doing this for you. But you would record all of the digits, all of the values that the electronic balance reports to you when you weigh any object on it. All right, now let's calculate the area of our rectangle. Simple formula, length times width. If I use the two values here, which have the least amount of significant figures, each of these values has what we call one significant figure, right? The sig figs are the values that we know for certain in a measurement, plus any reported values that are the guess, the uncertainty. So each of these had 1. This value has 2 sig figs, and this value has 3 sig figs. This becomes a bit of a sticky problem when we now go to combine our numbers. To get the area based on these two values, it would be our 0.4 times our 0.2, or 0.08 meters squared. If I report the area using these two values, it would be 0.35 times 0.234, or 0.0819 meters squared. The question is there a real difference between these two values, and are we actually done with our answers at this point? Are we ready to report them? We are over here, because each of our values had only one significant figure. Therefore, when we multiply, the rule is the product, the answer of our multiplication, has as many significant figures as the value with the least. No worries here, because each had one sig fig, so our answer has only 1. The 8 is a significant figure. This 0 is not a significant figure. It's just holding place, telling us that the 8 is in the 100ths spot, right? Not the 10th spot. Over here, though, we combine a number with two significant figures, with a number with 3 significant figures. And the result, therefore, can only have 2 significant figures. So we should round this to 0.082 meters squared. So we're able to report a different area for the same object depending on the tools that we use to measure the object itself and the properties of the object. Does that mean the area changed? No. Our ability to correctly and accurately report it changed with the tools that we used. And today's laboratory exercise will demonstrate that to you as you use tools like this meter stick and a few other instruments in the laboratory to measure lengths, widths, heights, volumes, masses, and combine those measurements using the rules of significant figures. And so you'll see that you're able to report a more accurate or less accurate result depending on which tool you used to measure the parameters and the properties of the object. Let me do one other example for you. I've drawn a little tree here with some apples or fruit on it, if you want to imagine the black dots as that. This is going to demonstrate how we calculate significant figures when we add values together as opposed to multiplying them together. Let's say we were charged with counting the pieces of fruit, and you counted the fruit that is on the ground. Well, it's pretty quick and easy to see that you have a total of 9 pieces of fruit on the ground. Okay? I'll count the ones that are up in the tree, and I've looked at that and quickly counted that it's 13. If this was a real tree, though, I might have missed 1 or 2 pieces of fruit if they were hiding in the leaves, up in the branches of the tree. Reasonable, right? This 3, in other words, is our guess, right? It's our sort of an unknown. I'm certain that I've passed 10, okay? And I stopped at 13, maybe it was 14, okay? So in a measurement, we've got that guess place. So now the total number of apples becomes 13 plus 9, or 22. The rule for addition is that the last value of our measurement, okay, we must end in the same place. Ones, tens, 100ths, for example, or tenths, 100ths, 1000ths, okay? That's what I mean by place. We must end in that place where our value with the least amount of accuracy ended. Here, they both ended in the ones, so our result also ends in the 1, and we can report 22. What if we had another tree, and I won't draw it though, where someone counted in the tree, let's say 130 apples, or they estimated it. The 3, according to our rules for significant figures, the 3 would be the guess place, unless they told us that the 0 was a guess, that they accurately, or they estimated that 0. They probably were counting by tens, and so they sort of visually grouped and counted by tens. And under this tree, we saw 15 apples on the ground. So our 5 is our guess. When we add these two values, because the 130 has uncertainty here, as soon as we add this 10 to it, this 4 now has uncertainty in it. So we need to stop there, because the rules of significant figures and measurement say that your value always ends with the uncertain place, and only one of them. So we would round this up, according to the 5, to 150 pieces of fruit. Okay? And the 5 being now an uncertain value ends our measurement or our result that we've calculated in this instance. Okay? So when we multiply, we track the total significant figures in the values being multiplied or divided. And when we add, we pay attention to where the last significant figure is, and we can't go beyond the least accurate of those positions. All right? So let's apply those then to the pre-lab questions that you see in your laboratory manual. Hopefully you have your laboratory manual out and are ready to answer these pre-lab questions. The first question asks you to just report how many significant figures are in each measurement. 4.50 centimeters, 0.0083 centimeters, and 2.030 millimeters. Sorry, the second one is in meters. So this value, when we report a 0 after the decimal place at the end of a measurement, that means someone has actually guessed it. That is their estimation or their guess. So that 0 is significant, and this would have 3 significant figures. But in this second case, these first 2 zeros are really just holding the place. This is a measurement I can tell that was made on side D of this ruler, for example, where the millimeters are marked out. This 8 would be in the millimeters position, and they have estimated that the value fell somewhere between the 8 millimeter and 9 millimeter mark. And so maybe at 8.3 is where they estimated the answer to be. This has only 2 significant figures, as these zeros don't count. In this last measurement, anytime a 0 is trapped between 2 other numbers, it is significant, so it counts. And again, just like our first example, this 0 ends our number after the decimal place, therefore it's significant. This has 4 sig figs in it. If we look at question 2, without drawing the entire scale, this object that we're measuring falls somewhere between 6 and 7. And the tenths are marked out. Therefore, we are going to have to at least report the whole number, 6. We can see that it goes beyond the 2. Now we estimate. Where does it fall between the 2 and the 3? We are required by good practices in chemistry and science to guess. So any number is reasonable. This is open for interpretation. I might guess 3. You might guess 4 or 5. Okay? What's important is that you put that number there. The difference is 2 or 3 significant figures in your answer, and then you can see how that would propagate into any calculation involving that number. Our last pre-lab question, let's calculate an area again. We have a area will be our length times our width, just like we did with our rectangle earlier. The length of our object is 23.7 centimeters. The width is 160.1 millimeters. I'm going to convert that to the same unit, so that's 16.01 centimeters. My calculator tells me that this answer is 379.437 centimeters squared. Units are part of the answer. My calculator doesn't understand significant figures, though. I need to interpret now. This value had 3, and this value had 4. When multiplying, our answer can only have as many figures as the value in our calculation with the fewest, 3. So we're going to round this, the 4, okay, 1, 2, 3 places. The next place over, which is a 4, would tell us to round down 379 centimeters squared. Thanks for watching today's video on fundamentals of measurement. Look for your next video on density part 1 and to get you ready for that experiment as well. Have a great day and enjoy the lab exercise.